All right, let's get started here in this video. We're going to cover 4.4, where we're going to look at concavity of slope of curves and then how to actually sketch these curves. So basically graphing. And we're going to go through here and we're going to kind of learn ways where we can do graphing a little easier than the memorization methods we did a lot of in pre-calculus. So let's start by looking at the example f of x equals x cubed. What does the first derivative test tell us about the function? Well, what does it tell us? It tells us the rate of change. That's one thing. Remember, rate of change is typically how quickly it's changing per time, or the amount it changes per time. It'll tell us if the function is increasing or decreasing, right? And it'll also tell us what the slopes of the tangent lines are at different locations. All right, so let's continue to look at this one. What if we want to know about the rate of change of the rate of change? In other words, the rate of change of the derivative. Well, that means we have to take a derivative of the derivative. So if we start with y equals x cubed, we take one derivative and we get 3x squared. If we want to know the rate of change of that derivative, we take another derivative and get the second derivative, 6x. All right, and when we do this, what this second derivative is telling us is it's telling us how much or in what way the slopes are changing as we move through the graph. So if we start over here on the left and we go walking in this direction, we walk from left to right, which is always how we're basically looking at graphs, you can see that over here we have a tangent. It's pretty steep. But as we move from like this point over to this point to the next points, I know I kind of put them far apart just so we could see it easier, you see that our slope has rotated in the clockwise direction. And if we move along a little further and we put another tangent line in, you see that we're still rotating in the clockwise direction. Now, if you remember, clockwise direction is actually the negative direction for changing angles. We want to go, like when we looked on our unit circle, right? Or anything like that, you start at 0 here and you measure around this way. You measure around counterclockwise. Counterclockwise is the positive direction. This is clockwise, so it's a negative direction. So what that tells us is essentially if we started doing the second derivative in this area, we would get negative answers because our slope is rotating counterclockwise as we move along it. And we call this kind of an area concave down right there. All right, it's concave down in that area. Now, if we look at the next part, if we continue walking, maybe I'll zoom in on this or something so the green's easier to see. If we look here, right, and we draw in our tangent line, we have a slope that's not very steep. And as we move to points further to the right, our slope is going to get steeper, right? And if we keep moving, it's getting even steeper. And so if you look at this, our slope is rotating counterclockwise, which is rotating in the positive direction. This means that over here, y double prime is going to be a positive value, and we call this concave up, okay, in that area where it's curved up, just like that. Okay, so take some time to make sure you're thinking about that. Draw some other curves and see if you can do this. The way I would show you this in person is I would actually put my pencil or pin along the graph, like where I was drawing these lines, and say maybe, I would put my pin down like this. Well, let me draw another curve. Let's say I had some curve like this. I'd put my pencil on here like that, right? And there we go. As I'd move, I'd just move my pencil on the curve, keeping it tangent to it, and show you that as you move your pencil along and keep it tangent like this, okay, that it's going to have my pencil is going to be rotating counterclockwise, or I'm sorry, clockwise at that point, but some point over here, it's going to start to rotate in the clockwise or counterclockwise direction. It's going to start to rotate this way as my pencil moves along it. So you can kind of do that if you're sitting there working on this on paper or something, is you can just move your pencil along it, keeping your pencil or your pen tangent to it at every point, and then just look and see. As you watch your pen or pencil move, is it rotating clockwise, is it rotating counterclockwise? If it's rotating clockwise, it is concave down in that area, and the second derivatives are going to be negative in that area. If it's rotating counterclockwise, it is concave up in that area, and your second derivatives are going to be positive in that area. All right, moving on here. This leads us to the second derivative test for concavity. The graph of a differentiable function y equals f of x is A, concave up on an open interval I if f prime is increasing on I. In other words, if f prime is increasing, i.e. that means f double prime is positive. And the concave down is if f double prime is negative, if it's decreasing. So we have a second derivative test for concavity. Let y equal f of x be twice differentiable on an interval I. If f double prime is greater than 0 on I, the graph of f over I is concave up. If f double prime is less than 0 on I, the graph of f over I is concave down. So in other words, greater than 0 meaning positive, and less than 0 meaning negative, right there. So if we look at this graph right here, you can see that there is nothing. Why does that keep? Anyway, you can see that as you move along here, right, on these little points, that the slope is always rotating counterclockwise. Okay, I started with this slope up here, and then I went to this one. That's a counterclockwise rotation. And then this one, all counterclockwise rotations. And even after we pass this point, we continue on up here, we continue, and they're all counterclockwise rotations as we move through it. And so that makes it concave up, and it's concave up on both sides, like a bowl, and there you have it. All right, and that's just for the graph x squared, which actually, if we do this real quick, look, f prime of x equals 2x, f double prime of x equals 2. And so no matter what, everywhere for the second derivative, it is 2, which means it's always, the rate of change of the rate of change is always 2, which means it doesn't matter what point we look at, it's always going to be a positive second derivative, which means, you know, we have concave up the entire way. All right, points of inflection. A point where the graph of a function has a tangent line and where the concavity changes is a point of inflection. So first you have to actually have a tangent line at that point. It can't be you can't be some jump in the graph or anything like that. And it's where the concavity changes. That's a point of inflection. So if we look over here, we can try this one. So determine the concavity of y equals 3 plus sine x on 0 to 2 pi. Excuse me, I don't know why I'm having to do that so much. Apologies. So let's look at this. First off, y prime, our first derivative. Well, the derivative of 3 is 0. And then the derivative of sine is cosine. So that's what we have. Second derivative is going to be just the derivative of cosine, and that's negative sine x right there. So where does our second derivative equal 0? All right, that's an important thing. That's going to tell us when the rate of change goes to 0, because we're going to need that for the concavity to change. So let's take a look. Negative sine x equals 0. That means that sine of x equals 0. That means x equals 0, pi, and 2 pi. So these are the places where we should look to see. So if we look to the left of these positions, so we can't really look to the left of 0 because we're between 0 and 2 pi. So we're between here and here, over here on the graph. So we need to look at the concavity from 0 to pi, and that's to the left. And we need to look, that's the left-hand side of the graph, and we need to look on the right, to the right from pi to 2 pi. So we need to look in those regions and see what is the, what's going on there. And so we look, f double prime of pi over 2 is negative sine of pi over 2, just like that. And the sine of pi over 2 is 1, and so we have to take the negative of it, so it's negative 1. That tells us concave down over that interval, and there's no change in the second derivative in there, so it's concave down that entire area. So we might say this is concave down, that's this section right here. And you can see it is concave down in that area. And then the next one is to the right. We can do f double prime of 3 pi over 2. That's something between pi and 2 pi. So that's going to be negative sine of 3 pi over 2. So again, think unit circle. 3 pi over 2 is negative 1. So this is negative of negative 1, which is just positive 1, which is concave up. And I'll do that one here in blue. That's this one. And that's this whole area right in here. Okay? So those are our two areas right there, and that is all concave up during that little interval. You can also take a look at the actual graph here of negative sine x right there, our second derivative right there, and it's this right here. You can see it right there, and it's telling us all in this area over here, we have negative second derivatives, which means all in that area here, we have all concave down because the second derivatives are all negative. And then in the next little section, we have all positive values right there. And so there we have all concave ups to 0 to 2 pi, just like that. Okay? And I know I guess our graphs extend a little beyond that, so ignore that part over there. But anyway, all that area, we have concave up where we have positive second derivatives. Okay? So be sure you, again, spend some time thinking about it and taking a look at it. So let's take a look at this one, finding inflection points. So what I'm going to do is leave this one for you to try. You have to be a little careful here, but give it a try and see what happens, and I'll put it worked out for you. What I will do is fill in this bottom part for you, just to give you a little hint of what you should look out for in this one. At a point of inflection, C, f of C, either f double prime of C equals 0 or f double prime of C is undefined. Okay, so give this one a try, and I'll put it worked out in the notes for you to take a look at, just so we don't end up with too horribly long of a video. All right, next, the second derivative test for local extrema. Here, this is where we can take a look to find out if we're looking at a local minimum or local maximum, or maybe neither, okay? So suppose f double prime is continuous on an open interval that contains x equals c. If f prime of c equals 0, if the first derivative equals 0, we know we have a horizontal tangent, and f double prime of c is greater than 0, then we have a local maximum. That would fit this example right here, okay? That fits that example, and you can see at this point we have a horizontal tangent. That gives us this being true. And then you can see that as we cross that point, we have positive slopes, less positive slope, horizontal, and then it starts going to negative slopes like that. So that tells us that our slopes are rotating this way as we travel across that point. All right, that is a clockwise direction of rotation for our slopes, our tangent lines, and that tells us that the second derivative is less than 0. It tells us that it is concave down, and therefore this point that we crossed, right, where we had a derivative equal to 0, has to be a local maximum. All right, it's a maximum when it's concave down because it's the top of a hill. On the next one, if f prime equals 0, again, this one's going to go with this situation right over here, the second one. So we're going to have this be true just by having this horizontal tangent right there. And then if the second derivative is positive, that means that as we cross, we're going from negative to 0 to positive slope. Our slopes are rotating around this way. They're rotating counterclockwise, which is a positive rotation, which gives us the positive slope, means we are down at the bottom. We are rotating in that direction, and therefore that gives us a second derivative greater than 0, and we have a local minimum. We're down at the bottom, like the bottom of a valley or something. Here, the third thing you have to look out for, though, is if the first derivative is 0 at that point, and the second derivative is 0 at that point, then the test fails. Then it fails. We don't know. We don't know if we have a local maximum, local minimum, or neither. And you have to do further investigation by looking on either side of the point to see what's going on. So in other words, plug critical points into the second derivative. All right. And you have to also note that it might be inconclusive. Okay, that's if both of them turn out to be 0. Okay, so let's try this right here. Apply the first and second derivative tests to the function y f of x equals x to the fourth, i.e. find the coordinates of any local extreme points and inflection points. What do you observe? So let's just go ahead and start by doing that and trying to graph this. So we have f of x equals x to the fourth, f prime of x equals 4x to the third, f double prime of x equals 12x squared. All right, so to find any critical points, we need to plug in the first derivative equals 0. So that tells us f prime of x equals 4x to the third, and we want to set that equal to 0. And this is going to be true when x to the third equals 0, or when just x equals 0. All right, so that tells us this point right here. This is our graph of it, pretending we didn't have that graph, but there it is. I'll note it for you. Right there, we have a critical point. So now we want to look at the second derivative at the critical point. So f double prime of x is 12x squared, and what is its value when we plug in that 0? It's 0. Okay? And so that's, let me write it this way so it's a little more clear. F double prime of 0 at that critical point is 0, which means, if you look back here, it has equal to 0, equal to 0. So we have inconclusive. So now we have inconclusive on whether or not that is an inflection point or a minimum or maximum value or whatever. So we're just not sure. So we need to look to either side of it. So we need to look from negative infinity. It's our only critical point. So negative infinity to 0. We'll look there first. So let's just do, we'll look at the slopes on there. So f prime of, let's try negative 1 equals 4 times negative 1 cubed. Negative 1 times negative 1 is 1, times negative 1 again is negative 1. So this is just negative 4. And that's a negative slope. That means we have negative slopes here, negative, 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 just like that. And then we're going to look from 0 to infinity. And when we look 0 to infinity, we see that we have f prime, and let's just do 1, equals 4 times 1 cubed. That's just 4. That's positive slope. So this is negative, and therefore decreasing. Here it's positive. and therefore increasing. That tells us then that we're going from a decreasing function to an increasing function. That tells us we have a minimum. So therefore, x equals 0 is a minimum. It's a local minimum. In fact, it's actually a global minimum. It's the only place where it changes direction, and we have that. If we look at the second derivative in these areas, so let me give myself a little more room here. All right, or maybe not, don't do that. I'm gonna just move it the other way. Therefore, because of that, that's a minimum. So if we continue looking though at this over here, what happens at the second derivative on that side? So let's do the second derivative at -2. That's 12 times -1 squared. That's just going to be 12. -1 squared is 1. Over here, I have f double prime. We can look at 1 again. That's 12 times 1 squared. That's 12. And so you'll notice here that we ended up with positive and positive. Okay? Positive means that it is rotating, that as we move through these different tangent lines, tangent, 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 we're rotating in the counterclockwise direction. And then that is also true on this side. We are rotating through the counterclockwise direction like that. And so we have positive rotations on both sides, which tells us that both are concave up. That tells us concave up, that tells us concave up. All right? So there is one for you. The next one I'm going to leave for you to try. I want you to find any coordinates of any local extreme points and inflection points, and then think about what you observe, and then graph this out on a graphing calculator or on Wolfram Alpha. Graph it and see what it looks like, and see if your points match up with what you see. All right, so let's just move on to then what's the purpose of this stuff. Well, we can put in a little pre-calculus and some calculus and end up, I mean, perfect might be a bit of an exaggeration, but really good graphs. All right, so this is curve sketching. So here's your procedure for curve sketching. What you want to do is identify the domain of f and any symmetries the curve may have. So that's from pre-calculus. Is it even, is it odd, anything like that. You want to find the derivatives, the first derivative and the second derivative. Find critical points of f, if any, and identify the function's behavior at each one. Find where the curve is increasing and where it is decreasing. Find the points of inflection, if any occur, and determine the concavity of the curve. Identify any asymptotes that may exist. You have to go back to section 2.6 for that, and plot key points such as the intercepts and points found in steps 3 through 5. So that's, again, back to pre-calculus. All right, so a line y equals b is a horizontal asymptote of the graph of a function y equals f of x. All right, and then a vertical asymptote, this is from that section, is if x equals a is a vertical asymptote of the graph of the function y equals f of x is either going to plus or minus infinity. So just take a look. We did these with limits back in the day, so you can find your asymptotes. But basically, it's a nice procedure for getting really good graphs, and you don't have to do a lot of memorization. It's a lot of just thinking through, well, what is the derivative telling me? What points can I come up with? And it will help you a lot. So I'm going to go through and try this next one, and then we'll see how it goes. So sketch the graph of the function x to the fourth minus 4x cubed plus 10x using the above steps. So first thing we want to do is identify the domain and any symmetries the curve may have. Well, this is not even, it's not odd. The domain is going to be all real numbers, so I don't have to worry too much about that one at this point. And then the next step says find the derivatives. So that's what we'll do next, is find the derivatives of this. And then after that, we've got to start looking at those points. So let's do that first. sorry here. All right, so let's do the derivatives first. First derivative is going to be 4x to the third minus 12x squared, and then the derivative of the 10 is 0. Our second derivative is going to be 12x squared minus 24x. So there's our first and second derivatives. So what we want to do is go ahead and find those critical points. And we can do that by setting the first derivative equal to 0. So let's do critical points. All right. And so that's f prime of x equals 4x cubed minus 12x squared. And so we're going to set that equal to 0. So first thing we can do is factor out an x squared and have 4x minus 12. And so either x squared equals 0 or 4x minus 12 equals 0. Either one of those will give us an answer. And so this one will give us -3, right? Add 12 to both sides, then divide by 4. And so there we go. We have our 2 points there, x equals 0 and x equals -3. And those are our 2 main points there that get this for us. Sorry, I feel like I'm missing a point here. Missing a critical point here. I was expecting 3, not -3. Oh, maybe that's because I have to add 12 to both sides, so that should be a +3. Sorry about that. There we go. All right. So now we have x equals 0, x equals 0. That's more like what I was thinking. So anyway, that gives us our 2 critical points, and so that's the first thing to look at. So we found our critical points and identify the function's behavior at each one. So in other words, is it, well, obviously what we have are tangent lines that are horizontal, but is it concave up? Is it concave down there? So let's take a look at the second derivative at those points. So second derivative at 0 is 12 times 0 squared minus 24 times 0. And that's just 0. So it's inconclusive for us there. But if we look at the second derivative at x equals 3, this is 12 times 3 squared minus 24 times 3. 24 times 3 is like 75, or 72. And 12 times 3 squared, well, 3 squared is 9. 12 times 9 is going to be over 100. So what is it, 108? And so this is going to be something positive. And therefore, if that is positive, we know it is concave up. We know that this is a minimum. Okay? So that tells us this is a minimum value right there. But we're inconclusive here. Inconclusive. Okay, we're inconclusive. So, bringing that down here, we need to look on either side at the derivative and see what's happening. So let's look somewhere between -infinity and 0, and we'll look at that first derivative. And so we'll go with what? -1. 4 times -1 cubed minus 12 times -1 squared. So -1 cubed is negative, so this is -4. -1 squared is positive, so minus 12, this is -16. So here we have a negative slope. So here it's decreasing. And then if we look from 0, and we don't want to go past 3, so let's look from 0 to 3, right? Because 3 was our other point. So from 0 to 3, let's just do f prime of 1. This is 4 times 1 cubed minus 12 times 1 squared, just like that. And we end up with 4 minus 12, which is also still negative, right? It's negative 8. And so this is also decreasing. So what we see here is our slopes are not changing sign. In other words, we're coming along with a negative slope, we're going to a 0 slope, and then after that point, after x equals 0, we're going back to being a negative slope. And therefore, this tells us that x equals 0 is a point of inflection, right? So if you remember, a point of inflection, where was it? That's finding inflection point, is where the concavity changes. All right. And so that's what we've got there. Because we're coming along, and, well, it's going to be a lot easier when we actually draw it to kind of show this to you. The concavity on the left side is concave up, and the concavity on the right-hand side is going to be concave down as we continue. That's how we keep that negative slopes going, okay? Otherwise, we wouldn't be able to go to 0 and then return back to negative. In other words, we have to have negative slopes that are rotating like this. They're rotating, and they're sloped down, so we have this concave up, and then we hit this horizontal slope, and then the slopes have to start going back to negative, which makes concave down. Does that make sense? Maybe, yeah. I wanted to show you that in drawing it on the actual picture, but it's like that. That's what happens when we don't have a change. When we have a slope of 0, but we don't have a change in the actual line of the slopes across that point where we had a derivative of 0. All right, so the next thing is to find, well, we know where it's increasing and decreasing. In fact, since this is concave up, since this is a minimum here, we know that it's decreasing, and we know that from 3 to infinity, it's got to be increasing, because it's a minimum, so we went from decreasing to increasing across there. Next, we had the point of inflection. We found it. There's not going to be any asymptotes because we don't have anything. We don't have anything in that graph that's going to make us anything undefined, or it's just going to blow up to infinity in both directions because of the x to the 4th. And now we're going to plot some key points, if we know any x-intercepts or y-intercepts, so we can check for that. Like, where is y equal to 0? So 0 equals x to the 4th minus 4x cubed plus 10. So you can go through it and you could find those. I'm not going to spend time doing that, but go through and find wherever that is, and you'd get the x-intercepts. You can also then, find x-intercepts, and then you can also go through and find where y is when x is 0. So this would be 0 to the 4th minus 4 times 0 to the 3rd plus 10. So obviously that's just going to be a 10, so that one's pretty easy for find a y-intercept. But anyway, you're going to find these points and you're going to go do it. I'm going to sketch it a little lighter here just because this is getting really long. And so when you do that, we can go through and put in all these little key points that we found, and you can take a look at this. So at x equals 0, we already know we need to be at 10, so we'll be up here. We know that we have a minimum at x equals 3, so you can do f of 3, and we can find out what that is. 3 to the 4th minus 4 times 3 to the 3rd plus 10. And so this is going to be 81 minus, what is that? It's going to be 112, I believe, and then plus 10. So this is 21, I think. All right, double check me on that. That can't be right. If we plug it in 3 to the 4th, let me try it. I'm going to do it on the calculator real quick. Let me get it turned on here. Let's do 3 to the 4th minus 4 times 27 plus 10, negative 17. Well, I was way off on that. Oh yeah, well, yeah, that's because the negative is greater. I don't know what I'm, sorry, having some simple algebra. So we're going to be down here 3 negative 17, and we'll have a point like this. And so what we would do is draw this in. We'd have an inflection point where we go to a horizontal slope right there, and then back to negative slopes. We'd have to come down and cross that. You'd have to find that. I'm not going to find it. It will curve back up there, and we'll go up this way. And so we'd have basically the graph. And if you found these two intercepts from right here, then you'd have it pretty well done. Okay? After this is a bunch of just some ones for you to try. And then the very last one on the ones for you to try, I want you to try and then take a look and see how I put it in there. It's about finding some variables in there that, you know, where you just don't know the coefficients, but you know some places where it has maximum and minimum. So take a look at what I do on that one, and I'll work the rest of these out for you. If you need any of them worked out in person, just let me know during our meetings, and I will take care of doing that for you. All right, but for that, that's pretty much it for this video. Thanks a lot. Bye.